Hello everybody, welcome to the AI Club. I am Shrutika. I am having around 13 plus years of experience in IT field under various domains and technologies. Worked with various companies like Infi, Accenture, Mindtree, and now I am working as a freelance trainer. So today we are going to talk about multivariate linear regression. So before the concept, let us consider what are the assumptions, and these assumptions hold good for both single as well as the multivariate regression. So the first concept is linearity, which is quite obvious. That is the relationship between the x and the y needs to be linear. And then the second assumption is homoscedasticity. So according to the definition, it means that the variance of residual is the same for any value of x. Okay, but further we will probe into this concept in our next slide. Before that, let us see the other assumptions. The other assumption is one is the independency. So with independency, we mean that the rows as well as the columns are independent of each other. So now let us understand both of them one by one. Let us say we have a .csv file having n number of rows and p number of columns. Okay, so independency of rows means that each row will be independent of all the other rows, and independency of columns means if there are p columns, p independent features, then each feature will be independent of the other features. Okay, and then the final assumption is the normality, that is for any fixed value of x, y is normally distributed. The error epsilon must be normally distributed. So what does this it mean is, when we have created the model and we start predicting the values, now the residual is the difference of the actual value and the predicted value. So when we start getting the residuals for n number of different observations, then these residuals need to be normally distributed. We will further discuss into these concepts as we move ahead. Now, coming back to the assumption of homoscedasticity, okay, or the opposite of homoscedasticity is heteroscedasticity. Now, as you can see in the slide, okay, the first graph, it shows the residuals on the y-axis and the fitted values on the x-axis. So as you can see, there is some kind of pattern that the scatter plot is making. Okay, so the pattern is something like, as the value of x is increasing, the value of residuals is also increasing. This is called as heteroscedasticity. And if you see the scatter plot which is just beside the first graph, you will see that the residuals are randomly distributed along the y as well as the x-axis. This means that there is no pattern existing in the residuals. Okay, that is called a homoscedasticity. So ideally speaking, when we have achieved a good model, then the residuals that we are able to get, they should be randomly distributed and there should not be any pattern. If at all we are able to see a pattern, it means the model needs to be further improved, because still there is some pattern existing in the data which can be extracted to create a better model. So let us move further. These assumptions and concepts we have to discuss in great detail as we move along. So now the thing is, what is multiple linear regression? Why it is required, and so many questions around it. So far we have learned linear regression with only one input variable. Okay, so single linear regression where there will be one dependent variable and one independent variable. Okay, what if you have multiple independent variables? How do you make a predictive model in such a case? And is multiple linear regression the solution in this case? So let us see. Uh, need of multiple linear regression. That is, why is it needed? Let us discuss all these things. So most of the concepts in multiple linear regression are quite similar to those in simple linear regression. Okay, so as you can see the equation in the slide, it says that y is equal to beta 0 but plus beta 1 x1 plus beta 2 x2, and it is going on till beta p xp, and then some error epsilon we are able to see. Okay, so this is a typical equation that is created for the multiple linear regression. So if you observe, it is somewhat similar to the simple linear regression equation. Only the thing is, it is having some more features, that is x2, and which is going on till xp, which is but obvious because we have multiple independent variables. That is why we are able to see all those variables in this equation also. So you can see that the equation for multiple linear regression is getting a bit complex as compared to the equation for the single linear regression. So what is different here from simple linear regression? We saw that the equation, it is somewhat similar. The only thing is, in multiple linear regression, it is getting a bit complex because the number of independent features is also getting more. So if you would have seen the session for a single linear regression, there you would have seen that there is a line of best fit. Okay, but in this case, instead of the line, we will be getting a plane of best fit. Okay, so if you can see this graph, on one axis we have years of education, on the second axis we have seniority, and these two are working as independent features to get the dependent feature, that is the income. Okay, so the income is dependent on years of education as well as the seniority. So as you can see, instead of a line, we are able to get a plane of best fit in case of multivariate linear regression. Okay, so the model in case of multiple linear regression fits a hyperplane instead of a line, which was the case in case of simple linear regression. And we still get the coefficients by minimizing the sum of squared errors, the least squares criteria. Okay, so that thing holds good for multiple linear regression also. If you remember, in single linear regression, we had a line called y equal to mx plus c. That was the line of best fit, and we had arrived on that line using the by minimizing the sum of squared errors. So the same process holds good here also. Only the thing will be, the number of coefficients will be more because the number of features are more. Okay, and the following assumptions from simple linear regression still hold, that is zero mean of error terms, independent errors, and normally distributed error terms with constant variance. So we saw, uh, we had a comparative study between the single linear regression and the multivariate linear regression. Now let us see that what is there more in MLR that we need to consider. Okay, so one of the thing is overfitting. So as more variables are added, the model may become far too complex. Okay, so let us take a use case of a sales price for a house, and we will try to understand this concept from this use case. Now if it is a single linear regression, sales price will be the dependent variable, and let us say the area of the house, that is the independent variable, and we are able to arrive at a model to predict the sales price. Now in order to get better results, we started adding more features. Earlier we had only one feature, that is the area. Now we got some more features. For example, the locality, where the houses are situated, then the number of rooms, and then the builder who has created the houses. Okay, so let us say there are some 4 5 more features added to it. Now what will happen? Earlier there was a single equation for the model that was created, y equal to mx plus c, or y is equal to beta 0 plus beta 1 x1. Now the equation will become as y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, depending on the number of features that we have added. So as you can imagine, this equation is getting far more complex. Now, because the model is getting complex, the MLR model may memorize the training data and then it can fail to generalize. So what is the result of this? Then when the model works on the training data, we get very good accuracy. But when the model is used for the test data or the unseen data, then the accuracy falls down and the model fails, which is called overfitting. So we have to avoid overfitting. So we will see what all treatment is done on the data and the models to avoid overfitting. Apart from overfitting, we have another concept called as multicollinearity. So this is something that we had already discussed in the assumptions also. So multicollinearity is the association between input variables. Now, as we saw in our use case of sales price for houses, okay, here we have one feature as area, and the another feature is the number of rooms. Now, if you can see, there is some relationship between the area and the number of rooms. Okay. Generally, if the area is more, the number of rooms will be more. So these kind of relationships, if they are existing between the features, the independent features, then the accuracy goes down and the model uh, doesn't work that good. So we have to remove that kind of multicollinearity. And the third point to consider is feature selection. Now, in this use case of our sales price for houses, we have seen maximum we have taken around 4-5 features. But when you go to a runtime scenario, you may get as large as 300 features. And at that time, if you simply create the model for all these 300 features, one of the things is the model will become very, very complex. The training time will for the model will increase. It will ask for a lot of CPU and RAM, and it may fail actually. So that is the reason generally, if we are getting so many features, then we try to drop some of the features and select only the features which are very, very important and which are impacting the dependent variables um, uh, very highly. Okay, so this feature selection criteria is very important. So selecting the most important features that contribute to R squared. So this we have to consider when we are going for MLR. So coming back to multicollinearity in linear regression, let us dive deep into this concept, what exactly it is, if we consider it from mathematical point of view. So the first point says that in regression, multicollinearity refers to predictors that are correlated with other predictors. So you can see some equations like x1 is equal to 2x3 plus 8x2, x2 is equal to 3x5 plus 6x3, etc. Okay, so as you can see, x1 is dependent on the values of x3 and x2. At the same time, x2 is depending on x5 and x3. Okay, so there is some kind of collinearity which is existing between x1 and x3 and x2, as well as x2 and x5 and x3. So if this kind of relationship is existing, we say that there is multicollinearity. And multicollinearity occurs when your model includes multiple factors that are correlated not just to your response variable, but also to each other. That is what we discussed right now. Then it results when you have factors that are a bit redundant or related to each other. In such a case, we can safely drop related variables and it will not affect our analysis. So when you are creating the model, there will be some signals which will tell you that there is some multicollinearity which is existing in the model, and you need to be concerned about that. So let us see what those signals are. Okay, the one of the signal is a regression coefficient is not significant, even though theoretically that variable should be highly correlated with y. What does this mean is, we have created a model, and subsequently we have created an equation for the model, given by y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on. Now let us say business tells us that the feature x1 is a very important feature in predicting the value of y. But when we see the equation, we see that the coefficient corresponding to the x1, that is beta 1, it is having comparatively lower value. So this is something which tells us that our model needs to be improved, because if feature is very significant, then the corresponding regression coefficient value will be more, and vice versa. So this we have to check when we are arriving to our model. Then the next thing is, when you add or delete an x variable, the regression coefficients change dramatically. Now, while creating the model, we come to know that, let us say, some two features are there which are not very important for our model, and we drop those features. And then when again we create the model, we see that the beta coefficients have changed dramatically. So again, it tells us that there is some collinearity going on between the features which we need to check. Then you see a negative regression coefficient when your response should increase along with x. For example, let us say the area and the sales price. If the area is increasing, generally the sales price increases. Okay, so this is a kind of relationship between the area and the sales price. And when we arrive at the equation, if the beta coefficient corresponding to the area, if it is negative, it means that our model is not correct. Some problem is there with our model. At the same time, if we have positive regression coefficient and the response should decrease as x increases, this also tells us that we need to work on our model again. And your x variables have high pairwise correlations. Okay, so these are the few points, few indicators which will tell us that we need to improve upon our model. So in order to remove the multicollinearity between various features, we use one of the techniques which is called the VIF analysis. So VIF, the full form is variance inference factor. Okay, and it is given by 1 by 1 minus r square. And this factor is used to know if there is any multicollinearity between the variables. So we will further probe into these things during our hands-on exercises also. So let us move ahead. Now, how to treat multicollinearity. Now we are having some libraries, inbuilt libraries, which we can use to find VIF factor for each of the features in our data set. Now, the statistical software calculates a VIF for each independent variable. VIF starts at 1 and have no upper limit. So it will be an integer value which will start from 1, and it can go up to anything, up to infinity it can go. And a value of 1 indicates that there is no correlation between this independent variable and any others. Okay, and VIFs between 1 and 5 suggests that there is a moderate correlation, but it is not severe enough. And VIFs greater than 5 represents critical levels of multicollinearity. And for VIF greater than 5, the coefficients are poorly estimated and the p-values are questionable. So generally, we will calculate the VIFs for all the features, and we will go through those VIF factors one by one. And then slowly, depending on our domain knowledge also, we will start dropping the features which are having high VIF factors, and then again we will calculate the model for the remaining of features. So in this way, recursively, we will go on creating the model, calculating the VIFs, dropping the features until we receive some acceptable values of VIFs, p values, and some other parameters. So this was all about how to treat data, how to make the model better when it comes to creating the MLR model. Okay, apart from that also, there will be some more treatment that is to be done for the data. One of this is the categorical variables. Okay, so again, let us take our use case of sales price. Now, in the sales price, as we saw, uh, the sales price was the dependent variable, and we had some features, let us say area, the number of rooms, the locality, the builder, the rating of the builder, let us say. So these are the independent features. Now, when we come to the making the model, now area is the numeric number. So this is it will work all right. Again, the number of rooms, it is going to be the numeric number, which is also going to be all right. When it comes to the locality, so it is not going to be a continuous number. Definitely it is going to be some kind of string. And as you know, the computers cannot understand string, and it has to be converted into a numeric or a binary variable. So this would be well known for the students of computer science also. When we are creating any program in any language, let us say C, C++, .NET. So when it is compiled and before running the program, actually each and every string variable, all the commands, everything gets converted to the binary format. So because the CPUs and the computer cannot understand the string variables. So that is the reason here also we will be converting all the strings to some binary or some integer variable. So which is called as the encoding of variables. So wherever you see that the feature is of type object or string, definitely we need to encode that features. So let us say there are actually a lot of encodings, and we will generally be using dummy encoding in our examples. So in order to understand what is dummy encoding, see in the slide, if you can see, okay, the one of the columns is the level of race, which can have the value of Hispanic, Asian, African American, and white. Okay, now because these are the strings and the computer cannot understand it, we have to encode it. In order to encode it, we used dummy encoding. And when we are using dummy encoding, it will create a few more columns in the data. Okay, so here the level of race, it is having 4 unique values. If you can see, Hispanic, Asian, African American, and white. So these are the 4 unique values. So depending on the parameters that we are providing to the function, it will create either 3 or 4 new variables. And as you can see here, if the value of level of race is Hispanic, okay, then the first variable one is 1 and the others are 0. Okay, so in this way we are coming to know that the value of level of race is Hispanic. Similarly, Asian is encoded as 010, African American is encoded as 001, and white is encoded at 000. Okay, so in this way we have encoded the unique values of level of race feature. So this is the kind of demo encoding which we'll be using for our hands-on exercises also. So apart from dummy encoding, there are some other kinds of encodings also, like label encoding or ordinal encoding. Then one hot encoding is there, effect encoding, binary encoding, base and hash target. But as of now, we'll be using dummy encoding only. So after this encoding, there is one more concept which we need to understand, that is the scaling. So what is scaling and why scaling? Okay, now to ensure that the gradient descent moves smoothly towards the minima and that the steps for gradient descent are updated at the same rate for all the features, we scale the data before feeding it to the model. So what if we come to layman terms, in layman language, if we have to explain scaling, then what exactly the scaling is? We convert all the data to the same scale. Okay, so that when the model starts working on the data, then it can treat all the features in the same way. So in some layman words, we can understand it like that, that scaling is also one of the important treatment which we apply to our variables before building a model. So we can also say that scaling can be understood as bringing data for all the variables to the same scale. So there are two types of scaling. One is the standardization and one is the min-max scaling. In standardization, basically brings all of the data into a standard normal distribution with mean 0 and standard deviation is equal to 1. And in min-max scaling, on the other hand, brings all of the data in the range of 0 and 1. So if you can see from the formula, if you have to use the standardization scaling, then we are first of all subtracting the mean of x from x, and then we are dividing it by the standard deviation of x. And if it is the min max scaling, then what we are doing is we are dividing we are first of all subtracting the minimum value from the x, and then we are dividing by the difference between the maximum and the minimum value. So in this way, we are just trying to bring all the data to a common scale. Now, scaling just affects the coefficients. Other parameters like t statistic, f statistic, p values, r squared, etc., they will not be affected. Now, so once after doing all these things, once our model is created, there are a few parameters which we need to understand in order to get that how our model is working. So model efficiency that can be determined using R squared parameter. So R squared, or sometimes we call as R2, explains the degree to which your input variables explain the variation of your output or the predicted variable. And then if R square is 0.8, it means 80% of the variation in the output variable is explained by the input variable. Okay, so in one way we can say that how better our model is working. This is somehow indicated by the value that R square is showing us. More the R square, the better our model is performing. But here one small problem is, if we add some more features to the model, then even if those features are redundant or if they are not necessary, still we will be getting the same value of R square, or sometimes it even increases, which is giving us a wrong indication that the model, there is no like a negative effect on the model when we are adding those features. But actually, if we see, if we are adding those features which are unnecessary, first of all, we are creating more complexity for the model. The training timing is increasing, it needs more CPU, it needs more memory. So that is why, ideally speaking, from holistic point of view, if we see, then the overall the quality of the model has decreased, but R square is not giving us any indication about that. So we have some another parameter called adjusted R squared, which gives us the indicator, a holistic point of view indicator, that how our model is working. So every time you add an independent variable to a model, the R squared increases even if the independent variable is insignificant. It never declines. And whereas adjusted R squared increases only when independent variable is significant and affects dependent variable. So if you can see, we have a formula to get adjusted R square, which is 1 minus this 1 minus R square n minus 1 by n minus p minus 1, where p is the number of predictors or the number of features. So all in all, if you see the number of predictors or the number of features as it is going into the denominator, it means that as the number of features is increasing, the value of R square adjusted is decreasing, which is an indicator that our model is not doing good. So we have to come up to an optimum model which gives us the best accuracy with minimum of features and minimum of complexity. So these conditions somewhere R square adjusted parameter is able to give us. Now which one to take, R square or adjusted R square? Now adjusted R squared is the real indicator of model efficiency, as just now we discussed about it. So in all our analysis with multiple linear regression, we will consider adjusted R square as the final measure of any model's efficiency. Now, one of the parameters that we had earlier discussed was feature selection procedure. If there are around 300 features that it is not possible to take all the features to create the model, then how to select the features? So this is called the feature selection procedure. For this, build the model with all the available features in the data set. Drop the features that are least useful in prediction. Look for high p-value for this thing. Then drop the features that are redundant. Look for correlations and VIF. Rebuild the model and repeat. And this process will go on till we start getting some good values for VIF, good values for p values. And then if we check the scatter plots of the residuals, that is also giving us a normal distribution. So these will be some of the indicators that our model has reached some optimum value. So that was all about the theory about the multivariate linear regression. In the next video, we will do some hands-on. We will explain some of the programs on multivariate linear regression, and there we will see how all these concepts have been practically used while programming and creating a good multivariate linear regression model. So thank you so much, and hope you had a good session and good understanding of this concept from this video. Thanks all.